Okay, thank you very much. Thanks to the organizers, Laura, Elio, and Thomas, for having me here, for having experiments represented, for having a female session, half session, um, and for giving me the chance to indeed speak about heavy fermion compounds, but not just heavy fermion compounds. I want to also highlight the beyond, because I think that the strange metal behavior that is very nicely seen in heavy fermion compounds actually is not a different kind of strange metal behavior than in any other material where you also have the strange metal phenomenon. And that's what I will try to convey in this talk. So this is ytterbium rhodium to silicon 2, a material that has already been highlighted in the talk of Jan van Delft. In fact, I thought I don't even have to give my talk because he gave already part of my talk, but let's take the real experimental perspective here. Okay, so there's a long list of collaborators. I'm very grateful to all of them. These are collaborators from Vienna, then many from Rice University, and some who have used our European microkelvin facility as users, who are, of course, also our collaborators. A lot of funding is needed for this research, as you know. So, strange metals, let me first focus on what is most famous about strange metals. It's their linear in temperature resistivity. And people in the heavy fermion community have pioneered these beautiful color-coded phase diagrams where the exponent of the temperature dependence of the resistivity is coded in color. And that is shown in all these examples here. And even though each group picks a different color for their strange metal, like orange here, yellow here, green here, red here, it's always the same. It's strange metallicity coming from essentially a point, if you just extrapolate this to 0 temperature. So somewhere on the non-thermal control parameter axis, there seems to be a point where this strange metallicity emerges from. And away from that, we have something much more normal. And that's much more normal in terms of resistivity is just the canonical T-square behavior of a fermi-liquid. So that is typically seen away from this quantum critical point. It's not very normal by itself because the renormalization in this fermi-liquid is very, very large. The effective mass, in fact, when you go to this quantum critical point, is diverging from both sides. But still, the most exotic thing that then emerges is that non-Fermi liquid behavior, which is not a Fermi liquid. So it's a strange metal and it's linear in temperature. That's what is seen in these materials. So that's many heavy fermion compounds, but it's not stopping here, of course, as you know. There are many transition metal compounds that show that behavior too. Transition metal oxides, an example for the cuprates, where it's sort of a bit less obvious that this comes from a point. Looks like there's a range of dopings where you find this linear and temperature resistivity, iron pnictides, and also organics. So it's a very broad phenomenon found in many different material classes. Also in material classes that have typically not been associated with this kind of physics, like F and D orbital systems, you know, there is some degree of localization in them, and their Coulomb interaction is very important. That's why we are here. We are discussing this physics here, but there is also linear and temperature resistivity in apparently totally different materials classes, such as magic angle twisted bilayer graphene, or certain Kagome metals, which do not necessarily have these very strongly correlated electron physics looking from far away, but they also have this phenomenon. And there is some emerging evidence that local degrees of freedom are in fact also very important there. And I will show a cartoon of this in a minute. Before doing that, let's look at real data, because color-coded phase diagrams are not beloved by everyone because you can sort of, looks a little bit dirty sometimes. Let's look at real data. So this is resistivity versus temperature, zoomed in at low temperature, zoomed in at higher temperature. It's as linear as you want. If you want to make it a very strong case, you can look at the logarithmic derivative of the resistivity on a log T scale, and then you see how wide this linear resistivity really holds in terms of temperature. And we heard that I think 3 or more orders of magnitude were found in these NRG calculations. That's actually not more than we see in experiment. It's just the same. We have like 3.5 orders of magnitude of linear and temperature resistivity in this material, as you can see here, from about 20 Kelvin to a few millikelvin. So it's a very, very robust phenomenon. Look at some other curves, that's cuprates, where the linearity really extends to very low temperatures. Of course, you have to put a large field to kill the superconductivity, but if you do, you see that linearity down to very low temperatures. An organic compound where the same is seen at a critical pressure, you see that linear resistivity extends to very low temperatures if you just kill the superconductivity. This is a magic angle twisted bilayer graphene, where it's also shown on a very sensitive plot, a log-log plot, where this slope here corresponds to linear resistivity. And you see that it extends also there to really very low temperatures. So the pronon argument doesn't seem very convincing if you have data which look like this. This is the Kagome metal of Georgi Kalsky's group, where that linear resistivity extends to somewhat higher temperatures. Okay, so these all have this phenomenon, and as I indicated already, evidence is emerging, or the idea is emerging, that perhaps the physics of all these systems are not so distinct. So in heavy fermion compounds, of course, we know what the building blocks are. There are these very localized F orbitals. They hybridize with the conduction electrons, as seen in the talks already this morning. In the cuprates, of course, some people like the single band Hubbard model, but many admit that it's actually likely that there is some more ingredients are needed. That's sort of the gray shaded thing here, maybe T prime or something else. So there is some localized and some perhaps more itinerant degree of freedom. And in magic angle twisted bilayer graphene, there is even quite elaborate mapping of the situation to a Condo lattice. And it's sort of this super lattice that is formed by the Moray pattern that localizes electrons on these on this Moray pattern. And then in addition, there are conduction electrons. Likewise, in these Kagome or other so-called line graph materials or frustrated materials, you have localization via motion, via destructive interference of electrons wanting to hop to different sites, but interfering so that the charge localizes. So perhaps all these systems actually share similar ingredients, which is the presence of both localized and itinerant degrees of freedom. So let's come back to strange metal resistivity. You could perhaps say, well, there's a million of ways to get linear and temperature resistivity. It's not so easy. In fact, it was already shown quite a long time ago that if you have, for instance, let's associate it with, there's a magnetic phase forming, at least in heavy fermion systems, this strange metallicity frequently arises where a magnetic phase disappears, then perhaps it's just scattering from this forming order that creates the linear resistivity, but in fact it doesn't. So the scattering of an antiferromagnetic order would only affect a small fraction of the electrons in the system, only around these hot areas or lines. They would be affected, but in the rest of the Fermi surface, they would actually not see these fluctuations from the order parameter, and thus this would short circuit the contribution to resistivity. And thus, in the case of low disorder, you actually fall back to T-square resistivity. You need very large disorder in order to see deviations from a normal T-square resistivity, but actually linear resistivity is not found in this treatment. There is a model that's very much discussed at present, the so-called SYK and related models that have extreme disorder in the interactions. So essentially every site interacts with every site, and it's fully disordered. that can be solved, and linear resistivity comes out of that model. So it's an option, but of course it's not a necessity that systems obey this model. Then another model that was also discussed this morning is the so-called Condo destruction, or sometimes referred to Condo breakdown model, which you see a cartoon of here. You have the intact Condo quasi-particles on one side of this quantum critical point, and they break up on the other side. And then as the local moments appear, they can order. They don't actually have to order. And that was the model, as you saw this morning, that actually they stay disordered and form, for instance, a spin liquid. So that's a possibility. But here you see the situation if then the local moments actually order. So many people have worked on this problem, but it's of course a very hard problem and hard to solve. And thus the results that we saw this morning are really extremely interesting to us, because NRG apparently can solve such a model and get real predictions or real calculations. Okay, so what can we do in order to discriminate between theory 1, 2, 3, 4, 5? We should come up with more experimental facts that a given theory should explain, so that we understand what's really the underlying physics. So resistivity alone will unlikely be sufficient to discriminate between the right and the wrong ingredients. So let's look at other things. I will touch upon very briefly the issue of Planckian dissipation, fermivolume jump, dynamical scaling, shot noise, and then unconventional superconductivity and other emergent phases. And step through this using always the ytterbium rhodium to silicon 2 as our study case, but then allude to similar properties in other systems that may then indicate that that's really what we are searching for, is a description for a very general phenomenon, not just a heavy fermion model. Okay, Planckian dissipation, it was proposed that actually we don't have to worry at all about what the microscopic understanding is. Linear and resistivity is there because we are hitting a boundary of maximal scattering dictated by the shortest possible time, which is Planckian time. So that would mean that all materials that have linear resistivity, if it's driven by that, by just running into this boundary, would have to obey that boundary. And that was suggested by this plot, where this line actually corresponds to this Planckian limit, where you have the maximal possible scattering rate. That's linear in temperature. For heavy fermion compounds, this was done, extracted from quantum oscillation data. And we looked at that from a different perspective, together with a postdoc of mine, Mathieu Taupin. We used electrical transport to infer the two ingredients that one actually needs in order to determine alpha. So it's a simple Drude model. You may wonder whether that makes any sense, because we are talking about a strange metal. Nevertheless, that's what was done. What you need to know in order to determine this alpha is the effective mass and the charge carrier concentration. You can try to get that from quantum oscillations, but we did something else. We got it from transport, so from resistivity in the Fermi liquid regime and Hall effect. And if we do that, we see that we do actually not run into this Planckian limit. The Planckian line is here, the alpha equal 1. But we do it for the heavy fermion compounds in the whole range where they are Fermi liquid, far away from the strange metal behavior, up to very close. And very close means the effective mass goes strongly up, velocity goes strongly down. So the point that is closest to the strange metal is the furthest away from the strange metal limit. Let me put it in a different plot, which is more intuitive. This is just the alpha. So this should be 1 if you want this to be Planckian. And what we see is the ranges of quantum Fermi liquid behavior, where we can extract this quantity, are pretty far away from that limit here. And they are in particular extremely far away if we pick the point that is closest to the strange metal, where the effective mass is largest. Okay, I don't want to imply too much from this, because it's a simple estimate. It's based on a Drude model, which maybe we shouldn't be using at all. It's not clear whether we should actually look at these strongly enhanced effective masses in this context. The only point I want to make is to say it's not fixed the problem. I think there is many issues here, and I would feel it's too comfortable to say, oh, you know, it's just Planckian dissipation. Let's pick another problem. Okay, so what is there in addition? The Hall, the jump of the Fermi volume was already alluded to today. These were the original data showing the Hall resistivity versus magnetic field, which is the tuning parameter in the system. It shows a jump in the sense that if you fit these crossovers, which are at finite temperature, to some phenomenological form, you can extract a width of the crossover, and this width extrapolates to zero, so to mean extreme infinite sharpness in the zero temperature limit. So it's a jump in the extrapolated zero temperature limit, which we call a Fermi volume jump at t equals 0. Okay, so this jump really occurs in the phase diagram exactly where we have the strange metal. So let's put the strange metal in here. That's the orange in this case. Across this line here, so sort of in here, that's where the Fermi surface reconstructs. So it's something that is directly related to the linear in temperature resistivity. And the model behind is the Condo destruction scenario, where this Fermi surface reconstruction is due to the fact that the Condo quasi-particles are intact on one side of that quantum critical point, but they break up on the other side because they are only, the F moments are only incorporated when they are part of the quasi-particle. One side has a large Fermi surface, while when they disintegrate, of course, they can't be part of the Fermi surface. The Fermi surface is small, and that's the origin of this jump in the Fermi surface. Just because quantum oscillations were mentioned this morning, quantum oscillations in principle are a great means to infer Fermi surface reconstructions. However, in this case, the magnetic field that is needed to resolve anything in quantum oscillations is much too large to observe this phenomenon, because we have a magnetic field-driven quantum critical point at very small fields, and the data that are available in the literature are at fields that are 2 orders of magnitude too large to be relevant for the quantum critical point. So yes, in principle, it's very valuable. And in some of the heavy fermion systems, it has indeed been used, which have larger energy scales. But for this material, there is no answer unless someone comes up with very, very advanced quantum oscillation experiments in ultra small fields. Jumps of the Fermi surface have been seen also in other materials. This is the heavy fermion compound I showed. This is another heavy fermion compound. There is this evidence or hint at a jump in the cuprates, of course, assembled over many materials and not extrapolated to zero temperature sharpness, but there is clear indication that something is happening to the Fermi surface near the optimum TC. And this is a plot in the supplementary information of one of Pablo's papers, where he pointed out that they have such a Hall transition also in magic angle twisted bilayer graphene at some carrier concentration. So perhaps that is something that is related to strange metallicity in many different materials. Then let's come to dynamical scaling. Dynamical scaling in the spin susceptibility has been one of the very first pieces of evidence for this Condo destruction scenario. It was investigated in cerium copper 6 dope with gold. And the collapse of the data, if you plot them in a certain scaled way, is exactly in agreement with the prediction from this Condo destruction scenario for the dynamical spin susceptibility, including the critical exponent. This is 0.75, and that was predicted by the theory of Condo destruction by Chimiausi's group. What came later, much later, in fact, is a similar analysis of the optical conductivity, so the spin susceptibility, of course, probes the spin degree of freedom. If you believe in Condo destruction, the charge degree of freedom should actually do the very same, because they break up and then spin and charge are critical. So you should see dynamical scaling also in the current correlation function, which is measured by optical conductivity. It has not been measured for a long time because it's very challenging to do that in heavy fermion systems, which are metals. The optical conductivity cannot be very precisely measured in bulk single crystals at the relevant energy range, which here is the terahertz, or in fact, it would be great if we could even go to lower frequencies. And it required the availability of thin films to do this experiment in time domain in transmission spectroscopy, which avoids the need for Kramers chronic transformation and makes this much more precise. So this was done. We grew these single crystal epitaxial films in a molecular beam epitaxy chamber, and then teamed up with Jun Kono at Rice University and Xingwei Li, who actually did these experiments. And you have also seen this curve already. These are the original data of the real part of the optical conductivity. And then in the scaling format, where the scaling exponent here is 1, as already indicated. What this corresponds to is in the regime where frequency is 0, linear and temperature resistivity, but in the regime where temperature is much smaller than frequency, it actually implies, and you already see it, linear and frequency resistivity. Okay, so all that goes together. So we have linear and temperature resistivity, linear and frequency, optical conductivity, and that energy over temperature scaling with critical exponent 1. So it really means that what we see in the linear and temperature resistivity is a dynamic phenomenon. Interestingly, what we did in here, what you see here, this is intrinsic. We subtracted, as you do for DC resistivity, a residual resistivity. We did that also for the optical conductivity, following advice by one of our reviewers. And we went back to data on the cuprates where this was not done. So this type of scaling was tested there, but at low temperatures, which is when you go to high values of omega over T, there was strong deviation from this behavior. So we thought that that could possibly have been due to the fact that there was no residual conductivity subtracted here. And we stole some beautiful data that are now published in this publication here, and did that very same analysis using the residual, fitting a residual conductivity to the data, and see what happens if we do that. Actually, we have a very wide range of beautiful dynamical scaling in the optical conductivity of this cuprate, and also a linear in frequency optical resistivity. So that seems to be perhaps some universality across different material classes in this property. I think I run five more minutes. Okay. Yeah, so one more experiment that's the most recent we are having on this material, short noise. Short noise is noise that you measure across a constriction in a film or in a material. So we used our MBE grown thin films, and then at Rice University, now in the group of Doug Natelson, the students succeeded in developing an etching protocol that leaves the film totally intact, but makes a nanowire out of it. So we have a very narrow constriction now. And then we can do short noise measurements, which is apply a voltage that is large compared to KBT, which is a tricky situation. It's not easy to do that. And then measure the current fluctuations. And the current fluctuations, that kind of experiment has been used before, for instance, to detect fractional charge in the fractional quantum Hall regime, or to detect Cooper pairs in superconductors. So it somehow measures the granularity of the charge by looking at this Fano factor, which is the current noise divided by the expectation for simple Poissonian value here, 2EI. And there are predictions for different situations. The prediction that is relevant for us with our nanowire, with our material, if we were in a Fermi liquid, we should observe this value here of 0.433, which is square root of 3/4. That's the regime where we are, because we know that we are not dominated by phonon scattering in this situation, but by electron-electron scattering. But what we see instead of this value here, we see a much suppressed shot noise. And that much suppressed shot noise, we interpret it in terms of actually the absence of well-defined quasi-particles. Whatever quasi-particle you have, and regardless how strong the interactions are, so this holds really up to very, very large renormalizations, but Z in the Fermi liquid description should still be finite, then you should always get this value. But if you don't have quasi-particles, then of course you could expect a much lower value. And that's the interpretation of this, which well suggests that this strange metal is not driven by quasi-particles, as you might have guessed, but it's a very direct evidence of the lack of quasi-particles in that situation. So this experiment should definitely be done in other materials that also show strange metal behavior. It's not trivial to do that because you have a lot of device fabrication in there and have to make sure that your material is still your material, but it's definitely something to be done. The very last point, superconductivity. Of course, one of the reasons why we want to understand strange metallicity is because in the cuprates there is high TC superconductivity coming out. And again, that is a phenomenon seen in all these other materials, or in most of the other materials, right? In the pnictides, there's superconductivity. In the heavy fermions, there is. But in the one that we looked at so far, there wasn't, right? There's this orange fan, but there is no dome. But that problem is solved now. We had to go to very low temperatures. Actually, nuclear demagnetization, cryostat measurements, which go well below 10 millikelvin. And you see here the boundary of superconductivity as determined from electrical resistivity. What you see is that there is superconductivity still at the quantum critical point. It doesn't look like an obvious dome, but please be aware of the fact that this is magnetic field driven. So a magnetic field will ultimately always want to kill the superconductivity. The fact that it is still here is actually pretty amazing because it vastly overshoots orbital and Pauli limiting fields for this material as determined from this initial slope here. So it is a very large field superconductivity that one observes here. And we firmly believe that this is driven by the strange metallicity, so the quantum fluctuations associated with it. Other phases emergent. Yes, one more minute. Okay, so of course there is entropy accumulation, even though third law of thermodynamics is always valid. But if you plot the ratio of S over T, it is peaked at a quantum critical point. So it's in some way natural that the system builds new phases out of this situation. One is unconventional superconductivity, but in a very different situation where we also find strange metallicity in the inelastic neutron scattering, we actually have the impression that a phase of wild Condo semi-metal forms out of these quantum fluctuations, which bridges the field sort of to topological quantum materials. And that's a work we'll writing up very soon because I think it's very exciting. Okay, so summary outlook. Strange metallicity is there in many different material classes. There is indication or hope, perhaps even, that models that are common to all these materials could explain these phenomena. I'm not saying that you all have to work on Condo models or periodic Anderson models, but I think that there is a common ground. So I think that much of the phenomena that are seen here might have a common explanation across these platforms, perhaps by considering the interplay of localized and delocalized degrees of freedom. And yes, of course, we should do more experiments to guide you guys. Thank you.